Is about different types of discontinuities. The ones that you're responsible for are jump, removable, and vertical asymptotes or infinite discontinuities. I'm also going to talk a little bit about oscillating discontinuities, but you don't actually need to know those. So there are two big types of discontinuities. They're either removable or non-removable, first of all. Removable means that you can fix the problem by either adding a point or moving a point. A single point fixes the problem. So for this particular discontinuity, we've got a value of the function, but we also have a hole in the function. If we could just move this dot right here and fill in the gap and take it away from there, we would no longer have a discontinuity. That's removable. Key here is you have to be able to remove just a single you can fix the problem with a single point. There are three types of non-removable discontinuities. The first one is jump. Jump discontinuity means that my function is moving along and then it jumps to a different location. That's a jump discontinuity. An infinite discontinuity is one where you have a vertical asymptote, either where both ends are pointing up into the same direction or down in the same direction, or one end is pointing up and one is pointing down, or maybe just one is pointing up and the other one is not. It has a value. The last one is oscillating discontinuity. An oscillating discontinuity is one where your function is going back and forth so fast that you can't evaluate it. A discontinuity in general is you can't draw it without lifting up your pencil. So if you have a removable discontinuity, I can't draw this without lifting up my pencil because I have to fill in this dot and then come back to it. If I have a jump discontinuity, I can't draw it without lifting up my pencil because my pencil keeps jumping. For an infinite discontinuity, I have to get past that asymptote somehow, so I can't draw it without lifting it up. Oscillating discontinuity, I can't draw it without lifting up my pencil because I need infinite ink here as I go back and forth. So that's the problem with oscillating. I'm going to give you some examples of these types of discontinuities. So here's the first example. And as we look for where is this function discontinuous, the first thing we say, it's a rational function. It has division, and otherwise it's polynomials, like the numerator and the denominator are both quadratics. Well, I know quadratics are continuous, so I'm totally fine with the numerator and the denominator, but I do know that if I'm dividing by 0, that's going to cause a problem. So I'm going to look at where am I dividing by 0, and the way I'm going to start that is by factoring this function. So x squared minus 4 is the same thing as difference of two squares, would be x plus 2. My pen is behaving poorly. Times x minus 2. And then this would be x minus 3 times x minus 2, I believe. So if I look at that function, I'm dividing by 0 at x equals 3 and at x equals 2. The difference is that at x minus 2, so if I do the limit as x goes to 2, it has a value. It has a value of 4 over 1. It has a value of over negative 1. It has a value of negative 4. So at x equals 2, that discontinuity is a hole. If I cancel those factors out, I have a function that behaves just fine. At x equals 3, though, that factor doesn't cancel out. And so at x equals 3, I have an infinite discontinuity. Because if I plug 3 into my function, I get 5 divided by 0. 5 divided by 0 indicates that I have an asymptote. Whereas if I plug 2 into my function, I get 0 divided by 0, which indicates a hole. Here's a picture of this function graphed. So I just used Desmos and graphed it, but I also, because of the way Desmos graphs, I had to kind of play with that hole to make it evident, but there's a hole here at x equals -2. The value of it is -4, which we figured out. But there's a gap in our function there. And then there's also an asymptote at x equals 3. So here's our infinite discontinuity because of an asymptote at x equals 3. And so that's how that function looks when you graph it. This next example, this is a piecewise function. One piece of the function is a quadratic. Well, we know quadratics are continuous. And the other one is linear, has a slope of 2 and a y-intercept of 0. Well, we know linear functions are continuous. So the only place where we might have a discontinuity is at x equals 0. And the way we're going to tell whether we have a discontinuity at x equals 0 is we're going to examine the limit as x goes to 0 from both directions. So as x goes to 0 from the negative direction, I've got it would be x squared minus 1 because that's the piece of the piecewise function I would use. So that limit is -1. But if I take the limit as x goes to 0 from the positive direction, I have 2x there, and that would be 0. So since those two limits don't match, that limit doesn't exist, and I have a jump discontinuity. So at x equals 0, it's a jump discontinuity. Those two limits don't match. That's a jump discontinuity. And then this last one, if I pull out my grapher and graph it, I see that kind of infinite oscillation that's happening at 0. So at x equals 0, this is an oscillating discontinuity. Again, you don't need to know oscillating discontinuity. I just wanted you to see it because it's an actual type of discontinuity. So those are the types of discontinuities: oscillating, jump, where your two limits exist, but they're not the same number. Infinite, where your two limits are infinity or negative infinity or a mix of the two. A hole, where your limit is a number, but your function doesn't exist at that point. And I said hole, I should have said removable because that's the language we're using here for those types of discontinuity. A hole and a removable discontinuity are synonymous. All right, good luck.